Swayam Prabha. Digital India. Educated India.
Welcome to the class. In last class we were started for the illustration or calculations for the steam power cycle, where we started with the idea of Carnot cycle, and Carnot cycle was comprised of 4 processes as what we know. So we were given an example that there are certain temperature and pressures, or there is some operating pressure for the boiler, there is some operating pressure for the condenser, and for that we had to operate a Carnot cycle between those 2 pressures, and we have to find out certain performance parameters of the steam power plant. For all sake, we were given that the pressure of the boiler is 30 bar and pressure of the condenser is 0.04 bar. So these are the given things for us. So based upon that, we did calculate all the corner properties like entropy, enthalpy. Using that we found out turbine work, compressor work, we found out efficiency, net work, and then work ratio and specific steam consumption. We just have to remember that all the things were based upon 30 bar and 0.04 bar. So if we would have been given a pressure which is more than 30 bar, then we have to take the Carnot cycle like this. If we were given with a pressure lower than 30 bar, then we have to operate Carnot cycle like this. But if we would have been given a condenser pressure lower than 0.04 bar for the present case, then we have to take as per the pressure given. If this is a pressure, then our 1 and 4 points would come down. So there are different formats of the Carnot cycle which would operate inside the dome. Carnot cycle, as the constraint of its processes says, it cannot come out of the dome. So knowing these facts, we will analyze the Carnot cycle. Here efficiency of Carnot cycle can be increased by decreasing the condenser pressure. We know that efficiency of Carnot cycle is 1 minus T low temperature divided by T high temperature. Here T low temperature is the condenser temperature, and at this moment, as known to us, is this condenser pressure is the pressure which is a saturation pressure. So this process is phase change process. So we have same temperature. So if we can decrease this temperature, means we are decreasing the condenser temperature, then we can increase the efficiency of Carnot cycle. But the lowest possible condenser pressure has a limit. It is dependent upon 2 factors. First factor is temperature of heat sink. So here we mean that who is the element, who is the sink which is going to take the heat from the steam which is getting condensed. So if that temperature is in our control, then we can control the condenser saturation temperature, hence we can control the pressure in the condenser. But there is a problem that natural resources are generally used to condense the steam. So there will be natural resources based, like water from the river or water from the ocean would be fetched into the condenser, and then we will have condensation of the steam, and then that heat from the steam would go to the water, and then water would get heated in this heat exchange process. So since we take water from the natural resources, temperature of the natural resource would be around 20 to 30 degrees Celsius. So our pressure which is the condenser pressure has got a constraint that it has to be around 20 to 30 degrees Celsius temperature's saturation pressure, or the condenser pressure would be the pressure or the saturation pressure corresponding to 20 to 30 degree Celsius. Second is the temperature difference required for heat transfer. We can go very close to the temperature of the surrounding or ambience or natural resource in the condenser, but in that case if we make temperature difference low and low, we would need very large area of the condenser. So, as what we had seen earlier, that there are irreversibilities associated, here irreversibilities would practically lead to the point that we need larger area for heat transfer. We had discussed that the direction of the flow of water in the condenser is not going to alter the irreversibilities, but if we try to have the temperature difference between the natural resources based water and the steam to be minimum, then we will have very large area to be supplied for the process of condensation. Therefore, in general, process of condensation would be having temperature difference around 10 to 15 degrees Celsius. Therefore, lowest possible condenser temperature is 25 to 30 degrees Celsius, in that range. Hence, the condenser pressure becomes the corresponding saturation pressure, which we can obtain from the steam table. So, we can see here that if we reduce the condenser pressure, so condenser pressure actually reduces in this direction, we can see that efficiency increases as we decrease the condenser pressure for the given boiler pressure in the example. We have to remember that this plot is drawn for the example. Okay. So, we had given that there is 30 bar pressure of the boiler and there was 0.04 bar of the condenser. So, that 0.04 bar is decreased to different pressures. Thus, this is the one way in which we can improve the efficiency of Carnot cycle. We can as well increase the efficiency of Carnot cycle by increasing the boiler pressure. We again can go back and see the formula for Carnot cycle efficiency. It is basically 1 minus efficiency is equal to 1 minus T low divided by T high. And here we say that if we increase the boiler pressure, means boiler is the place where we are supplying the heat. So, we are increasing the temperature in which the heat is getting added. So, we are basically increasing the mean temperature of heat addition, and then that is why we will have increase in efficiency if we increase the boiler pressure and hence the saturation temperature and hence the mean temperature of heat addition. But there is a limit, and that limit says that the materials which are going to be exposed to that high temperature should not melt, and this is called as metallurgical limit, and we should not go beyond that metallurgical limit. But critical conditions for water are 374.15 degrees Celsius and 221.2 bar, and these are not too high as compared to the metallurgical limit, as compared to the melting point of the metals which are used for making the boiler material or making the boiler component or the turbine components. So, there is no much problem about the material limits in case of Carnot cycle, but yes, we cannot go higher than this condition, since we would come out of the dome and then the process of heat addition would not remain isothermal heat addition. Therefore, the critical condition cannot be crossed in case of Carnot cycle. Then how does efficiency change? Efficiency increases with increase in the boiler pressure and hence the boiler temperature for the given condenser pressure of 0.04 bar of our example. So, it is evident from the figure that if boiler pressure increases, we get higher and higher efficiency, but at higher boiler pressure there is a rate of increase of efficiency is low. But we have a problem that in case of increasing in efficiency, we have to increase the strength of the components which are going to have stress under the boiler's high pressure. So the cost also increases, but at higher pressure there is not much increase in the efficiency. So we have to have compromise between the increment in efficiency and the cost of fabrication of the components. But there is a thing what we can see, that there is large increase in specific steam consumption in case of Carnot cycle for the given example of 0.04 bar of 0.04 bar of condenser pressure. And this increase in specific steam consumption is basically due to the fact that we are having decrease in W net. We can see it from the steam tables that as we will increase the boiler pressure, the enthalpy difference between the boiler inlet and boiler outlet decreases. Basically that decrement is due to the decrease in latent heat of water which increase in the boiler pressure. And since latent heat decreases with increase in boiler pressure, we have actually lower W net into the Carnot cycle, and that lower W net actually increases the specific steam consumption. But although work W net is lower, equally Q in is also lower, so we have higher efficiency of the cycle. So if we would like to have operation of the Carnot cycle, then we have to have compromise between the specific steam consumption, between the cost of the fabrication and also with the efficiency. So we will solve, and now the same example but in different perspective, which states that we are given with 30 bar and 0.04 bar as the boiler and condenser pressures. We again have to find out efficiency and specific steam consumption, but now we are told that turbine and compressors are not ideal. Turbine and compressor efficiencies are 0.8 or 80%. So given this fact, we know now how to draw the Carnot cycle, and Carnot cycle here is again ideally 1, 2, 3, 4, 1, 2, 3, 4, where 0.2 and 0.3 are fixed ideally, and then we can find out 1 and 4, but there is a problem that we are told that efficiencies of pump and compressor are 80%. So we have to draw the real process in the pump and compressor. So we name that 1 to 2 is the process in the compressor and 3 to 4 is the process in the turbine. Actual process is 1 to 2, but ideal process is 1 to 2 dash. This is actual, this is ideal in case of compressor. In case of turbine, we have 3 to 4 is actual and 3 to 4 dash is ideal, and this is in case of turbine. So we again know that P2 is equal to P3, and this is given as 30 bar. So knowing this, we can know the properties at 0.2 dash and 0.3. So that having temperature 507, so we know that H2 is equal to HF, and then that basically H2 dash is equal to HF, and that is given to us as 1008 kilojoule per kg from the steam table. So we know that S2 dash is equal to S1 and S3 is equal to S4 dash. So these are the known things, so that we can find out enthalpies at 0.1 and 4. We know now the saturation temperature corresponding to 0.04 bar is T1 is equal to T4 is equal to 302 Kelvin. So we get X4 dash as 0.716 and X1 is 0.726. Till this step, the example is same as what we had solved for efficiency, which is 100%. Then we are supposed to find out enthalpy which is H4 dash, we know now this enthalpy is same which is earlier enthalpy. Based upon this X4 dash, it is 1863 kilojoule per kg Kelvin, 793. So we can get ideal turbine work as 940 and 215. So we can now find out what is the actual turbine work. Actual turbine work is 80% of ideal. So we get 752 as actual turbine work. Parallelly, ideal turbine work, compressor work divided by 0.08 is the actual compressor work. So we got actual compressor work also. Knowing this, we know now what is the W net. W net is turbine work minus compressor work, and this is 483. So we know Qn, Qin and Qin is H3 minus H2, and H2 enthalpy is to be calculated. So H2 enthalpy is based upon that we have H3 minus H2 is the 1741 as Qin. Knowing this, we can know what is the specific steam consumption, and specific steam consumption is 7.45 kg per kilowatt hour. So this is how we can solve the example which would be given to us for the conditions where we do not have ideal components. Thus we have found out all the necessary parameters which are required to be found out. Only one thing to be noted over here, that we were not knowing H2, which is the enthalpy required for calculation of Qin, but we can find out from the actual work of the compressor. So actual work of compressor is 269, but we know 269 kilojoule per kg is equal to H2 minus H1. Here we have found out H1, so we know H1, we know H2 minus H1, so we would have found out H2. So but H3 is also known, so H3 minus H2 is Qin. So this was one more thing to be noted over here. Otherwise, if we require, we can as well find out the entropy at 0.2, dryness fraction at 0.2 also. So by this we have found out parameters like specific steam consumption and W net. Knowing the Qin and W net, we can find out efficiency, and efficiency turns out to be 27.7% for the present example.